So this lesson is going to be lesson 7 from unit 1. This is going to involve proportion and direct and joint variation. So this is from chapter 8. This is going to be sections really 1, 2, and 3. So away we go here. So one of the things we've talked about a little bit in class is what's a proportion, and we'll again talk about it here as well. So proportion is an equation where each side can be represented as a fraction. So notice how each side is going to be represented by a fraction, which we also will call a ratio in that sense, because it's more like comparing two things. So we have what's called proportional concepts. So as I said, many real world situations are said to be proportional. So this problem solving strategy is going to be kind of important, especially in manufacturing. There's a lot of concepts in manufacturing that involve this proportional concept. So again, what a proportion is, it's when we have two fractions that are equal. If two fractions are equal, what also holds true is the cross products must be equal. So as we look at this here, 2/4 is the same thing as 1/2. And I can also prove that by using the cross products. The cross products have to be equal. So notice that 2 times 2 does equal 4 times 1 because they both equal 4. So notice how the left side and the right side are equal. So these fractions are said to be proportional as well. So in this section here, you'll start to see proportional equations. And we may have to round some of these to 4 decimal places. So we'll keep that in mind as we move forward in our assignment. So that's how, if we solve this, we can cross multiply to help us see this thing. So we know that 8 times 3x is going to be like 24x. And 16 times 3 is going to be 48. So basically, what you're trying to do is figure out 24 times what value gives me 48. If we're unsure there, we can divide each side by 24. And then that will allow us to get the coefficient of x to be a 1. So we just drop it. And notice that 24 does go into 48 twice, so x would equal 2. So no need to round that one. This next proportional equation, we have to multiply this 5 times this x minus 1. So 5 times the quantity x minus 1. And that's going to equal 4 times this x plus 6. So I'm going to put the 4 in front, it just looks better. Remember, with multiplication order does not matter. Remember, to solve an equation like this, we have to remove the parentheses. So we use the destroyer property to multiply the 5 through the parentheses. So this 5 has to go through there, and this 4 is going to have to go through there as well. So 5 times x is going to be 5x. 5 times -1 is going to be a -5. That's going to equal then 4 times x is going to be 4x. And 4 times 6 would be 24. So again, we want to get the x's on the same side of the equation. So I like to pick on the little guy. So between a 5x and a 4x, the 4x is smaller. So I want to zero the 4x out with its opposite. So I'm going to put a -4x there, as long as I put a -4x there. So in other words, we're subtracting 4x on both sides. So this gives me x minus 5 is equal to, then, since these 4x's will zero out, it just leaves me the 24. And if we had a 5 on both sides, we get x by itself. So x would equal then this 29. So that would be the solution to that equation. So number 3, notice how again we have a fraction equal to a fraction, or again, we call these proportions. And the strategy to solve these is to cross multiply. So I have this -5 times x, which is going to be -5x. And I have to multiply this 5 to this x minus 2. So I have this -5x, and we have multiply the 5x, the 5 through, that would give us 5x minus 10. So here I have to pick on little guy to get the x on the same side. So since this is -5x, I'm going to add a 5x to this side as long as I add a 5x to this side. So this is going to give me a 0 equals then 10x minus 10. So then I have to add a 10 on both sides. So it's going to give me 10 equals 10x. then I'm going to divide both sides by 10, and therefore 1 would equal x, or x would equal 1. So that would be my solution. So a solution with there would be a 1. So we could also write that as a solution set notation. So as we move into this next lesson here, this next question, I may need a calculator here, so hold on a second. So as we begin to solve this one, we cross multiply, have this 8 times x. I like to keep the variable on the left side if possible, so I'm going to put the 8x over here. Then I have to multiply this 9.12, so 9 and 1200ths times 1 and 300ths together. So I'm going to kind of slide this over and pull up my calculator. We'll clear that off there. So I have this 9.12 times then 1.03. And notice that's basically like saying 9 times 1, so the answer should be close to 9. So we have this 9.3936. So 9.3936. Oops. Let's see here. So again, to get x by itself, we still got to divide each side by an 8. So this looks like we may have to do some rounding. We'll see. So x is going to equal then, so 9.3936 is going to be divided by 8. So I have that in the calculus. So all I got to do is hit divided by 8. Notice how it has this a and s. It just brings down that 9.3936 down. If I divide that by 8, hit enter, that gives me 1.1742. So again, I don't have to round that one either. So 1.1742. So it would be our solution there. Again, if we need to write it as a solution set, we'd have 1.1742 as a solution set. So here we actually start to look at actual applications a little bit. So we have like a ratio of 12 kiloohms to 8 kiloohms. And we have X kiloohms to 6 kiloohms. So that probably should have had kiloohms there. So again, when we solve this algebraically, we can leave the units out for the time being. So I have 8 times x there, which is 8x. And then 12 times 6 would be like 72. And if I divide each side by an 8, x would equal then 9. And, you could say this is 9 kiloohms. You actually put the unit in there too. So you probably won't have to put the unit. The unit probably will be part of your answer. So all you got to do is probably put the 9 next to it. And the kiloohms should already be present. So that's when you want to start paying attention to the actual units of measurement, because that really gives the problem some life. So that's how we have 50 miles per 1 hour. And then we have 400 miles in so many hours. So we're trying to figure out how many hours it takes you to travel 400 miles, if that's the same speed as 50 miles in 1 hour. So again, I can actually solve this by using proportion math. So I have 50x equals then cross multiply, and 400 times 1 would just be 400. So if I divide each side by 50, x equals, and again, notice how these trailing zeros can divide out. So really it's just 40 divided by 5, which would be 8. So it'd take you about 8 hours to do that. So that makes sense. If you're driving 50 miles an hour, it would take you 8 hours to go 400 miles. So where this takes us to is what we call direct variation. So direct variation is when the relationship of 2 pairs of data affect each other directly. What this means is one piece of data increases, the other also increases. Similarly, if one piece of data decreases, the other one will decrease as well. So, one of the things we see on this is like, if my number of hours increase at work, then my salary is directly impacted by that. So my salary increases. So that would be an example of a direct variation. So we have things like that going on here. So one piece of data will be called the independent variable, and the second will be described as the dependent variable. So most often we're going to be looking for we're going to be given the independent variable, and we're going to be looking for the dependent variable. So a lot of times we have what's called input and output as well here. We'll talk about that later. So notice that the number of gallons purchased can be described as an independent variable, and the total cost will be described as the dependent variable. And notice that this is, if you don't buy much gas, then you don't have to pay too much. But if you buy a bunch of gas, then you're going to pay more. So the number of gallons purchased is going to directly impact your total cost of purchasing the gas. So the number of gallons purchased is considered the independent variable, and your total cost is described as the dependent variable. So usually the independent variable is what you're starting with. It's usually described as the input, what you're beginning with. The dependent variable is your output, or your result, if you will, your outcome. So solving direct variation problems, what we want to do is we want to establish two pairs of related data. What we want to do is write one pair of data in the numerators of the two ratios. We want to write the other pair of data in the denominators of the ratios. And this is going to form a proportion using the two ratios. So as you can see, we're going to start looking at some applications here. So notice a truck travels 102 miles in 6 gallons. How far will it travel on 30 gallons of gasoline? One thing to pick up on is this is a direct variation, because the more miles you travel, as your mileage increases, the number of gallons also increases. So this is kind of a direct variation. So as far as known facts go, what we pick up on is we know that there's going to be 102 miles and you'll be using 6 gallons of gas. So 102 miles uses 6 gallons of gasoline. Another thing is the unknown fact would be we have this, we don't know how many miles if we use 30 gallons of gas. Notice when I write my ratios, notice how I went miles to gallons. It's a good idea when you write the second pair, keep the same thing, miles to gallons. That'll kind of help it out here. So notice that, if I look at this pattern here, I went from 6 gallons to 30 gallons. So if I increase my number of gallons used by a factor of 5, my mileage should also increase by a factor of 5. So as an estimation, what I'm seeing is all I really have to do is multiply like 100 times 5. That'd give me like, 500 miles is what I'm picking up on there. So we can kind of see a pattern here that I increased by a factor of 5. So all I got to do really here is increase by a factor of 5, and that's going to give me my answer. So that's how I could actually use estimation. As a calculation goes, what we can do is, notice I have this 102 miles uses 6 gallons. This is going to be the numerators of my ratio, and the X miles to the 30 gallons is going to be my denominators of the ratio. So if I use my calculations, I'm going to have 102 miles, 6 gallons. So I have those equal. And on the bottom, I'm going to have X miles to 30 gallons. So from there, all I have to do is cross multiply. It's going to give me 6x. And then I have to figure out what 30 times 102 is. So 30 times 102. That's going to give me 3060. So x is going to equal 3060. If I divide each side by 6, that should give me my value for x. So I now just divide that by 6, I end up within 510. So x equals 510. And notice that estimation was around 500 miles. So that makes sense. So what I can do is I could pick up on that. My interpretation is I can, travel 510 miles on 30 gallons of gas. So that would be my interpretation. So there's also what's called the constant of variation. So to find the constant of direct variation, kind of the steps are identify a pair of data in which both values are known, and then write the data pair as a ratio. The units in the denominator of the ratio should match the units of the independent variable. And then leave the ratio as a fraction or change it to a decimal equivalent. So if we have a 15-ounce box of cereal costs $2.29, find the constant of direct variation to the nearest 10,000th of a dollar for the cost per ounce. This is also referred to as the unit cost. Okay. So again, notice that it says the units in the denominator of the ratio should match the units of the independent variable. So the independent variable is going to be in the denominator. Notice how it says the cost per ounce. So what they're saying is ounces is in the denominator. So this is telling me that my independent variable was the denominator. Usually X represents independent and Y usually represents dependent as we move forward. So notice how it says cost per ounce. So what this is kind of telling me is the numerator has to be the cost and the denominator has to be the ounces. And so what I'm looking for up here is where I know the cost and the ounces. So notice that we know that 15 ounces cost $2.29. So I can use that to create my constant, my direct variation constant. So the 229 would have to go on the top. And I have to divide that by 15. And that's going to allow me to get my constant of variation. So let's go ahead and put that in. So 2.29 divided by 15. That's going to give me then, so this 0.15267. So let's round this to like 4 decimal places. So that's going to be where that 6 is. This is going to be like 0.1527. Actually says to the nearest thousandth. So I have like I said 10,000th. So that is 4 decimal places. So what did I say there? So nearest 10,000th was the 4 decimal places. So 1527. So 0.1527. So it's going to be my constant variation around 4 decimal places, or in other words, the 10,000th place. So that's going to be what we call the constant of variation. And that's all it has to do is find that. So it's going to be basically, like a unit cost. So if I put that out there, it's going to be like roughly 15 cents per ounce is what that kind of boils down to if I run it to the nearest penny. So so if you go to Kroger's or somewhere, you'll see a unit cost. A lot of times that unit cost goes out 4 or 5 decimal places. So, but remember, 2 places how money works. So 15 cents per ounce is what that is. So the constant of variation, the constant of direct variation can be used to solve for missing values. And so notice how K was the constant of variation. If I use the formula y equals kx, I can actually solve direct variation problems. So notice how this formula here, k equals y over x. Notice how k is the constant of variation, and y over x, I'm looking for that known ratio to find the constant of direct variation. But then we're going to use this equation, y equals kx. That's going to be the formula for direct variation. So let's look at this question here. An architect's drawing is scaled at 0.25 inches and equals 5 feet. Find the actual measurements for the following measures shown on the drawing. So notice how this again is a direct variation problem, because we have 5 feet is 0.25 inches. If you increase the number of inches, the number of feet should also increase. So that is a direct variation problem. So to find the constant of direct variation, k equals y over x. So we're looking for some known values up there. And notice how it says find the actual measurements. So if we're looking for the actual measurements, that's going to be the 5 feet. So what we're looking for is actually going to be the what we call the output value. So that's going to actually represent the y value if we're looking for the actual measurements. So 0.25 inches is the scale, and the actual measurements is the feet. So using the so this is the part A, is you have this 0.75 inches. So what we're picking up on is, as far as using the constant of variation, k is going to equal, we have this y over x, where these are the two relationships we know. It's the 0.25 inches and the 5 feet. Notice the 5 feet is the part that we know. So the 5 feet would go here, and the 0.75 is going to be here. So since we're looking for the actual measurements, that's going to become what we call the output value, or y. So if I, let's see, it should be 5 divided by 0.25. So if I divide 5 by 0.25, I can come up with the constant of variation. So it's going to be 20. So basically, it's like 20 per 1, if you will. So it's going to be 20 feet per 1 inch, if I look at that as a ratio. And that makes sense, because 0.25 is like a quarter of an inch. If you multiply by 4, that would be 1 inch. If you multiply that 5 by 4, that would be 20 feet. So that kind of makes sense there. That's the constant of variation. So using the formula, I have y equals kx. So if I want to find the actual feet, we have y equals 20 times x, which was the 0.75 inches. That was our dependent variable. So if I multiply 20 by 0.75, that should give us that answer. So notice I got 20 in there, times then 0.75. That should give me the answer there, which would be 15 feet. So if the measurement on the drawing was 0.75 inches, the actual distance would be 15 feet. And that makes sense there as well, because that would be like 0.75 is like 3/4. So if I want to do the next problem, I have now 1.25 inches. So this is like part A. Part B, again, you're going to use y equals kx, where the constant of variation was the 20. And this time we have 1.25. So notice that this actually makes the math quicker if we're doing multiple problems. I don't have to set up a proportion every time. So I have 20 times 1.25. So that should be a little bit over 20 now, shouldn't it? So 20 times then 1.25. It's going to give me then 25. So 25 feet. So that's how we can solve a direct variation problem. So there's also what's called joint variation. When one quantity varies directly with two or more quantities, so I should say two or more quantities, this variation is described as joint variation. So we have this y equals kxz. So notice how y again is kind of the output. This is what we're going to be looking for. This is going to be the dependent variable. The k is going to be the constant of variation. The x and the z are going to be the given information. So k is the joint constant of variation. So what we have here is, find w if w varies jointly as x and y, and x equals 140, y equals 6, and the constant of joint variation is 0.5. So notice how, since we're trying to find w, that's our dependent variable, that's our output. The x and y become our independent variables. That's what's known. They give us the joint variation constant, which is this 0.5. So this just becomes then w equals this 0.5 times then this 140 times this 6. And that should give us our value for w. So we have 0.5 times 140 times 6. So it gives us then this 420. So an application also is the simple interest of an account is jointly proportional to the time and principal. If the quarterly interest for an account balance of $7,000 is $87.50, find the interest on the balance of $8,500 for 9 months. So we're looking for interest. So notice how interest is going to vary directly with the principal and the time. The more the principal and more the time is, the interest should be increasing as well. Or the smaller the principal, the smaller the time, the smaller the interest. So that's described as a direct variation. But now we have two things involved, principal and time. So this is called a joint direct variation problem. So again, we don't know the interest. The principal, they said, was 7,000. Let me see what we got here. Actually, they give us everything, but they don't give us the rate, do they? So we have some thinking to do here. So let's start with so to find the interest, we need to know the principal, the rate, and the time. So I'm kind of seeing two problems laid out here. The first one is we're talking about quarterly interest. Quarterly interest means we're talking every divide a year into 4 pieces, that'd be every 3 months, basically. So notice how they do give us a $7,000 balance, and they do give us they actually give us an interest of $87.50. They don't give us the rate, but they do give us this time of quarterly. So quarterly, again, is going to be 3 months, if you will. So we have that kind of going on here. So this information to start with if the quarterly interest for an account balance was $7,000 is $87.50. They give us all that, but what that allows us to find is what's called the interest rate. This is going to be the rate of interest. A lot of times this is going to be as a decimal or a percent. So we usually leave it in a decimal form since our calculator doesn't do percents. So when we do this, though, you remember time has to be in years. So, 3 months is not a whole year. So that's a fraction of years. That's like 3 out of 12. So if I divide 3 by 12, that's going to give us 0.25. So it's going to be a quarter of a year. That makes sense. So if we start substituting into our formula, 87.50 was our interest. The principal was 7,000. The rate we don't know. I'm going to just use X there. And the time is going to be actually a quarter. It's not a whole year. So 0.25. So if I clean this up a little bit, I have 87.50 is the interest. If I multiply the 7,000 times the 0.25, that gives us this 1750. So this is going to be 1750x. Now, if I divide both sides by 1750, so I have 8750 divided by 1750. So 87.50 divided by 1750. This should give us a decimal, so 0.05. So that's going to give us our interest rate, which is going to be at 0.05. So in other words, that's going to be like 5%. But we want to leave it as a decimal, 0.05. So what this allows me to do is this allows me to find the next level of this problem. It says find interest on $8,500 for 9 months. So part 2 of this problem is I can find the interest now because I use the other information to actually find the interest rate. So we can still use the principal times the rate times the time. Our principal now, though, is 8,500. Our rate was this 0.05. And the 9 months, notice again, that's not a whole year. That's 9/12 of a year. So that 9 months is like 9/12. If I go ahead and change that to a decimal, so 9 divided by 12, it looks like we should know that. Yeah, it's 0.75. It's 3/4 of a year. So let's just change that to a decimal. It's easier to put that into a calculator. So that's going to be 0.75 years. So notice how it's not a whole year. It's part of a year. So my time is actually going to be a fraction or decimal of a year. So if we put that all together, we can go then 8,500 times then the 0.05, which was our interest rate that we found, times then the 0.75. That gives us then $318.75. And so notice how the only thing that really changed was, we did $7,000 for, say, just a quarter of a year. Notice how interest was 0.75. Now we're moving up to 3/4 of a year. Notice that our interest actually increased a little bit because we also increased our investment, our principal. So that should make sense there in that problem there. So that gives you a little bit of insight of how direct variation works. So again, in word problems, there's this thing, direct variation, but to be a direct variation, as one value is increasing, the second value has to also be increasing, or vice versa. If one value is decreasing, the other value, the second value, has to be decreasing as well. There has to be this direct variation concept to it. So that concludes my lesson on direct variation as well.